Alright. Alright, so we need to read through 2 sections in the next 2.5 hours. I'm just going to read through them. Maybe we'll do some problems, but I don't really have time to do a ton of problems. Okay, alright. So 1.2 is on the analytic technique and separation of variables. Okay, what is a differential equation? A first-order differential equation is an equation for an unknown function in terms of its derivative. Why can't I zoom in? What the hell is going on? Okay. There are 3 types of variables. The independent variable, the dependent variables, and the parameters. Alright, so there's that. This terminology is standard but a bit confusing. The dependent variable is actually a function. So technically it should be called the dependent function. The standard form for a first-order differential equation is dy dt is equal to f of t and y. Here the right-hand side typically depends on both the dependent and independent variables, although we often encounter cases where either t or y is missing. A solution to the differential equation is a function of the independent variable that, when substituted into the equation as the dependent variable, satisfies the equation for all values of the independent variable. That is, y of t is a solution if it satisfies dy dt is equal to y prime equal to f of t, y of t. Okay. Alright. This terminology doesn't tell us how to find solution, but it does tell us how to check whether or not a candidate solution function is or is not a solution. Consider the differential equation y dot equals y. We can easily check that the function y1 of t is equal to 3e to the t is a solution. Because if we take dt of 3e to the t, we're going to get 3e to the t. So, therefore, so then this is equal to dy dt, and it's equal to y. So then it works. Sign, because it's not. It's clearly, it's not. Okay. Checking if we look at it more complicated. Then we have considerably more trouble finding a solution. On the other hand, if somebody hands us y of t, we know how to check whether it or not it is a solution. For example, suppose that we meet Paul, Bob, and Glenn. Or if we do 1 plus t in equal to y of t in dy dt is equal to y squared minus 1 over t squared plus 2t. So if we plug in for y of t, then we're going to get 1 plus t squared minus 1 over t squared plus 2t. So this is going to be t squared plus 2t plus 0 over t squared plus 2t. So this gives us 1. So that means that dy dt is equal to 1. If y is equal to 1 plus t, then dy dt is equal to 1. So it does check out. So now, but if we were to do this, 1 plus 2t, let's see, 1 plus 2t, let's try 1 plus 2t. 1 plus 2t squared is equal to 4t squared plus 4t plus 0 is equal to 2, or is equal to 4t t plus 1 over 4t plus 4 over t plus 2 is equal to dy dt. So that doesn't seem right. And then if we do 1, y of t equals 1, then we're going to get 0 Wait, so I feel like alright, so first they take the derivative and they get 1. Then they substitute it into the right hand side and they also get 1. Okay, so yeah, so this is what I got and this is wrong. But then the second one is right. Both the left hand side and the right hand side of the differential equation 0 for all times t. So Bob's is, Paul is, but fucking Glenn. God damn it, Glenn. You can't do anything right. Alright. The lessons we learned from this example are that a differential equation may have solutions that look very different from each other algebraically. And that, of course, not every function is a solution. Given a function, we can test whether it is a solution just by substituting it and seeing whether the left-hand side is equal to the right-hand side. So we can always check our answers. That's nice. Okay. IVPs. Okay, IVPs are important. All they are is a differential equation associated with and a single value for a single time point, and that allows you to find the constants. Okay. When we encounter differential equations in practice, they often come with initial conditions. We seek a solution of the given equation that assumes a given value at the particular time. A differential equation along with an initial condition is called an IVP. The usual form for an IVP is that. It's pretty obvious. You got a dy dt, and then you got a y of t0 equals something. Here we are looking for a function y of t that is a solution to the differential equation and assumes the value y is 0 for a time t. Often, the particular time in question is t is equal to 0, but it could be anything. Okay, then they just plug in. So they have this c here from the integration. Then they plug in y of 0. So 0 there, and then c. And then they find that c is 1. The general solution is one where you haven't removed the integration constant. So the general solution is there for like a family of functions, rather. Okay, separable equation. Now that we know how to check whether a given function is a solution to a differential equation, the question is, how do we get our hands on a solution in the first place? Unfortunately, it is rarely the case that we can find explicit solutions of differential equation. Many differential equations have solutions that cannot be expressed in terms of known functions such as polynomials, exponentials, or trigonometric functions. I really never understood that. However, there are a few special types of differential equations for which we can derive explicit solutions. In this section, we discuss one of these types of differential equations. It's given a first-order differential equation. A differential equation is separable if it's actually a function of t product a function of y. So then you can separate that out. So the simplest separable first-order differential equation that includes both the dependent and independent variable would be dy dt is equal to y of t. It's clearly separable. However, this is not separable because you can't write y plus t as a form of f of y times g of t, or however they had it, g of t, h of y, whatever. But you can't do it. Now this one, I think is, because you got t plus 1 over t times y plus 1. So this would be f of y would be equal to 1 over y plus 1, and g of t would be equal to t plus 1 over t, and then the product of those is that expression. So so here, and let's see, we'll see this right now. Yep, okay, so that's what I just said. So right, and here's the thing where obviously they're separable if they're either autonomous or not dependent on the variable at all. The dependent variable, that is. So let's just read it. Two important types of separable equations occur if either t or y is missing. So that's clearly separable because you can just write f of y as 1 and then it doesn't change anything. Dy dt is equal to h of y is also, this is the form of a y dot is equal to h of y is autonomous. Basically no dependence on time. So then they're just giving us an example that the original logistic equation for population growth is autonomous because there's no t on the right hand side. Okay. How to solve separable differential equations. To find explicit solutions of separable differential equations, we can use a technique familiar from calculus. Consider t over y squared. There's a temptation to solve this equation by simply integrating both sides with respect to t. Now we are stuck. We can't evaluate the integral on the right-hand side because we don't know the function y of t. Okay. Yeah, I really have stopped. I need to get back on my integral calculus thing because I am so bad at integrals right now. Now we are stuck. We can't evaluate the integral on the right-hand side. Okay, we need to do something to this equation before we try to integrate. Okay, so there you go. So you just move the y, and this allows you to separate it out. Okay, there we go. Yeah, and then you do some algebra and you get this thing, and then right, so then we just plug in the square and see that it all balances out. If you read the previous example closely, you probably became nervous at one point. Treating dt as a variable is a tip-off that something a little more complicated is actually going on. With a separable equation, we rewrote it as 1 over h of y dy dt is equal to g of t. This equation actually has a function of t on each side of the equal sign because y is a function of t. So we should write it as, 1 over h of y of t dy dt g of t. In this form, we can integrate both sides with respect to t to get. Now for the important step, we make a u substitution just as in calculus by replacing the function y of t by the new variable, say y. Hence, we can integrate the left-hand side with respect to y and the right-hand side with respect to t. Separating variables and multiplying both sides by the multiplying both sides of the differential equation by dt is simply a notational convention that helps us remember the method, but it is justified by the argument above. I need to review u sub. I don't remember u substitution at all. If it is possible to separate variables in a differential equation, it appears that solving the equation reduces to a matter of computing several integrals. This is true, but there are some hidden pitfalls. Consider... oh yeah, I wanted to look at this one. Y dot equals y squared. It's autonomous and hence separable. It looks easy. We're tempted to say that this is the general solution. However, we cannot solve all initial value problems with this solution. If we have y of 0 is equal to minus 1 over c, we can't... The equilibrium solution is not like in that. So y of 0 equals 0. I'm actually curious. So if we have, like, let's just say minus 1 over t is equal to y of t, then dy dt, so we have minus t to the minus 1. So we should get, this goes to 1 over t squared. Yeah, and that's true. Okay. Alright. Cool. So, if we take the derivative of this thing with respect to t, and then we plug it in for y, this in for y squared, we do end up getting the same thing out. Great. Anyway, so yeah, there's that. The right-hand side of the differential vanishes if y equals 0, so the constant function is a solution, but and it is this equilibrium solution that satisfies the IVP, y 0 equals 0, even though it is missing from the family of solutions that we obtained by separating variables. It is a solution that we need if we want to solve every IVP. So then the full set of solutions is not just y of t is equal to minus 1 t plus c for y of 0 equal to 0 for not equal to 0, and y of t is equal to 0. So that gives you everything. Alright, getting stuck. As another example, consider the differential equation y dot is equal to y over 1 plus y squared. We separate. We integrate. Okay, alright, so then there's cases with only implicit solutions, which is fine. That's fine, right? It's not the worst thing in the world if we have an implicit form for the solution. Even then, we didn't obtain explicit solutions by separating variables for this equation. We can find one solution if y equals 0. Yeah, that's true. So we do have the constant function, though. So again, because it doesn't appear in our implicit general solution, we still need to include that elsewhere. There is another problem that arises with this method. It is often impossible to perform the necessary integrations. Consider, okay, so wait, let me just write down some of these examples. So the implicit only example is y dot is equal to y over 1 plus y squared. Leads to ln of y plus y squared over 2 is equal to t plus c. Can't isolate y. Great. Alright. But then there's even worse cases, right? What? Even worse. dy dt is equal to sec y squared. Alright, for example, the differential equation is autonomous, separating variables and integrating. We get this. The integral on the left-hand side is difficult to say the least. In fact, there is a special function that was defined just to give us a name for this integral. The lesson is that even for autonomous equations, carrying out the required algebra or integration is frequently impossible. We will not be able to rely solely on analytic tools and explicit solutions when studying differential equations, even if we can separate variables. Alright, a simpler, or a savings model. I'm gonna get some more ice. Ice in my veins! Suppose we could deposit $5,000 into a savings account with interest accruing at the rate of 2% compounded continuously. Right. Okay, savings model. Compound continuous interest DE, let's say 2% cont is equal to y dot is equal to 0.002y. Alright. So we get the general solution with the exponential. Assuming interest rates never change, we get after 10 years. Why does it say 0.2 there? Is that... Oh, because 10 years? Okay. After 10 years, you only get $1,000? What the hell? 10 years you get $1,000, bro? I want more than that. The focus on this thing is so shitty. Okay. Mad money, bro. Mad money from the account each year in a continuous way beginning in year 10. Oh, interesting. Wait, is that the right model? I definitely want to look into this minus 500 thing, because how does the minus 500 mean every year? Okay, because this is... What is this? Okay. I didn't really get that, honestly. Alright, the name mixing problem refers to a large collection of different problems where two or more substances are mixed together at various rates. Alright, mixing problem. I'm gonna get some comfy clothes and some more ice. Let's see, how much more do we have? I think we have a lot more. Shit. I only have like an hour and 45 minutes. Alright. Mixing problems. Sounds cool. Consider a large vat containing sugar water. Okay. Alright, I'll read it out loud. Okay, consider a large vat containing sugar water that has been made into soft drinks. Suppose the vat contains 100 gallons of liquid. The amount flowing in is the same as the amount flowing out, so the total volume is constant. The vat is kept well mixed, so the sugar concentration is uniform throughout the vat. The sugar water containing 5 tablespoons of sugar per gallon enters the vat through pipe A at a rate of 2 gallons per minute. Sugar water containing 10 tablespoons of sugar per gallon enters the vat through pipe B at a rate of 1 gallon per minute. And sugar water leaves the vat at pipe C at a rate of 3 gallons per minute. To make the model, we let T be the time measured in minutes. Okay, so the sugar entering the vat comes from pipes A and B, can be easily computed by multiplying the number of gallons per minute of sugar mixture entering the vat by the amount of sugar per gallon. Right, all that's saying is that 5 tablespoons of sugar per minute. Okay, the amount of sugar leaving the vat, though, through pipe C at any given moment depends on the concentration of sugar in the vat at that moment. Okay, so the concentration is given. The concentration is given by S over 100. So the sugar leaving the vat okay, so they make the model now. So ds dt is equal to 2 gallon per minute times 5 tablespoons per gallon, which gives us 10 tablespoons per minute. Okay, then plus 1 gallon times, what is it, 10 TB per gal. And then we're subtracting, oh wow, okay, 3 gal per minute times S over 100. I'm pretty sure S is also in tablespoons. So that gives us S dot is equal to 2000 minus 3S over 100. Okay. I'll do the manual. Okay, so we get Let's see if I did that right. Oh, so they just divided that. That's smart. That's what you should do for sure. Okay, so instead of this, you just okay, and then they get let's see. So they integrate and they get ln 2000 minus 3s over minus 3. I'm gonna turn off my phone, man. Alright. Alright. Okay. Let's yeah, just more integration and answer the question. All right, so we're good here. Let's just read through some of the exercises. I'm not gonna actually do them, I think, just because. Well, maybe we'll do a couple. All right, so we got dy. This is gonna be 1. dy dt is equal to y plus 1 over t plus 1. So this is clearly separable, right? Where f of y is equal to y plus 1 and g of t is equal to t plus 1 to the minus 1. Now, we're going to get dy over y plus 1 is equal to dt over t plus 1. And I'm pretty sure that we get ln y plus 1 is equal to ln t plus 1. And then we x, but we get y plus 1 is equal to t plus 1. Y equals t. Is that true? Well, let's do the plug-in thing. All right, so Bob says y of t equals t. That's what I got. So let's say, so y of t equals t, dy dt equals 1. Okay? So if we plug in for y, then we in fact get that. So Bob is right. So A, Bob is right for sure. Now let's say Glenn. So Glenn, we're going to get 2 is equal to dy dt. And then if we plug in, we're going to get 2t plus 2 over t plus 1 is equal to 2 times t plus 1 over t plus 1. So this is right actually too. Glenn is also right. This is so weird to me. Introducing it like this, like I've never really done this before, but it's so weird. Okay, and Paul says y of t is equal to t squared minus 2 is equal to t minus square root of 2 t plus square root of 2, right? That's just factoring it. But let's first off do this. So we get y, t squared minus 2 plus 1 is equal to t squared minus 1 is equal to t plus 1, t minus 1. And so then we get over t plus 1, then we can cancel. Then we get, so t minus 1, y of t is equal to t minus 1. Or wait, no, this is dy dt. And if we do this, so no, I'm pretty sure Bob and Glenn are right, Paul is wrong. Okay, what solution should they have seen right away? Probably, I would assume they're saying the equilibrium solution y of t equals 0. B y of t equals 0. Alright. Okay, a bunch of integration problems. I actually want to do a lot of these at some point. I really got to stay up on it. Alright, let's just see if we can get the... Damn, I really want to do more of these exercises. Okay, but given that we only have an hour and a half, I'm just going to read 1.3. Oh, where's my LaCroix? Alright. Finding an analytic expression, in other words, finding a formula for a solution to a differential equation is often a useful way to describe a solution for a different equation. However, there are other ways to describe solutions, and these alternative representations are frequently easier to understand and use. In this section, we focus on geometric techniques for representing solutions, and we develop a method for visualizing the graphs of the solutions to the differential equation. The geometry. If the function y of t is a solution of dy dt equals f of t of y, t and y, and if its graph passes through the point t1, y1, okay, then the differential equation says that dy dt at t equal to t1 is given by f of t1 y1. So it's the slope of the tangent line. Okay? Note that there is nothing special about this point other than the fact that it is a point on the graph. So if this is a solution, then we evaluate... this is a solution of y of t. This is a plot of y of t. And then using f to compute the tangent slope. The equality must hold for all t. Okay. Slope fields. Slope fields, everyone. Come around. You get your slope fields. This simple geometric observation leads to our main device for the visualization of solutions to first-order differential equations. If we are given the function f and ty, if we are given the function f, we obtain a rough idea of the graphs of the solutions to the differential equation by sketching its corresponding slope field. We make this sketch by selecting points in the ty plane and computing the numbers f at these points. At each point ty selected, we use f of ty to draw a mini tangent line whose slope is f. These mini tangent lines are also called slope marks. Once we have a lot of slope marks, we can visualize the graphs of the solutions. I wonder if there is a... Let's see. quiver. Okay. All right. All right, and it's interesting that they choose this differential equation, dy dt is equal to y minus t, because it's not separable. In other words, the two right-hand side, the right-hand side of the differential equation is given by f of t and y equal to y minus t. To get some practice with the idea of a slope field, we generate a slope field by hand at a small number of points, and we discuss a computer-generated version of this slope field. Generating slope fields by hand is boring. Okay, so they do it by hand. All right, so let's see if this is finished. Okay, so we're gonna just do basically a slope field. All right, so f of t y is equal to y minus t. Okay, then let's just say we want, I don't know, 0 to 10. So then we want f dot no, but we want does that work? Okay. I think is that gonna work? Oh. What? There we go. So, what that's saying is that, let's look at the points. Oops. So at the point t equals 0, y equals 10, 0, 10, we're getting a slope of minus 10. Wait, is it y minus t or t minus y? Oh, it's y minus t. Oh, wait. Is that right? I think that's actually right. Okay, so we're good. So there's actually going to be a... Wait, what? That's at 1, 1. That's 0. Okay, yeah, that checks out. All right. Okay. Right, there should be a line. Wait, so if we look at we should see. So I did this wrong, sort of, I think. They don't actually correspond to. These would need to be. This need to be transposed. What if I did this? Bro, it's actually so stupid. Okay. Does that work? I think, though, I can do this. I don't know. Anyways, it's not important. I was just trying to see if I could see this thing, but I guess you can. You can. There we go. That's cool. I don't know if this is right. This should be 1 minus. Okay, well, minus 1. Whoa, what just happened? Okay. Alright. Okay, let's check it. Okay. So if y of t is equal to t plus 1 plus ce to the t, then dy dt is going to be equal to 1 plus ce to the t. And the answer was what? T minus y? Or y minus t? Y minus t, right? Yeah, y minus t. So if we plug in y there, we're gonna get t plus 1 plus ce to the t minus t. So this crosses out, and this becomes 1 plus ce to the t, and that is what we get. Alright, so that checks out. That we verified that's the solution. That's easy. Alright. Okay. All right. All right. So we're talking about special cases right now. We're talking about the homogeneous, or not the homogeneous, the autonomous case, which is this one, and this, which is, I don't know if this has a name. Okay. Slope fields for y dot equals f of t. Oh, right, yeah. As long as the t's are the same coordinate. Oh, yeah, that's interesting. Okay. Yeah, geometrically, this implies that all of the slope marks on each vertical line are parallel. Yeah, that checks out. So that's that. It's kind of light. You probably can't see it, but that makes sense. Whenever whenever a slope field has this geometric property for all vertical lines through, we know that the corresponding differential equation is really an equation of the form only of t. For example, consider the slope field shown in figure 1.17. Y dot equals 2t. Alright, that's a general solution. Okay. In figure 1.18, we have superimposed graphs of solutions. Note that all of these graphs differ by a vertical translation. If one graph is tangent to the slope field, we can get infinitely many graphs all tangent to the slope field. By translating... Oh, okay. Yeah, they're just speaking geometrically. I already understood what they meant from this comment. But this is an immediate consequence of it. If one graph is tangent to the slope field, we can get infinitely many graphs just by translating the C. Alright. Slope fields for an autonomous... Right, okay. This is the other case. In the case of an autonomous differential equation, y dot equals f of y, the right-hand side of the equation does not depend on t. The slope field in this case is somewhat special. Here, the slopes... So let me write this down. So, in the case where y dot equals f of t, the slope fields are y invariant or something. I don't know. But the point is that the slope will be so like the same for all t. The same f of right. Okay. Now here it's sort of the other way. The slopes that correspond to two different points with the same y coordinate in the autonomous case where y dot is equal to f of y, we have that for any 2 points with same y coordinate, the slope will be the same. Slope or deriv will be the same. Okay, cool. Alright, so let's look at this one. Wait. Wait, then why is this different? Oh, because y is different? Oh, but for the same one. Oh, okay, yeah. So these are the plots that you need to make. So okay. Yeah. Oh, there we go. There's that logistic equation. That's cool. Oh. What a beautiful graph. What a cool graph. By translating to the left or right. Okay. Analytic versus qualitative. Let's see how many pages we have left, by the way. So we're at 42. Okay, actually, we're pretty good. We only have like 4 pages left. Maybe I'll go on a walk or something before class. All right. Analytic versus qualitative. For the autonomous equation, y dot equals 4y times 1 minus y. We could have used the analytic techniques from the previous section to find explicit formulas for the solution. In fact, we can perform all of the required integrations to determine the general solution. However, these integrations are complicated and the formulas that result are by no means easy to interpret. This points out the power of geometric and qualitative methods for solving differential equations. With very little work, we gain a lot of insight into the behavior of solutions. Although we cannot use qualitative methods to answer specific questions, such as what the exact value of the solution is at any given time, we can use these methods to understand the long-term behavior of a solution. These ideas are especially important if the differential equation in question cannot be handled by analytic techniques. As an example, consider y dot equals e to the y squared over 10 sine squared y. Wait, is sine squared x equal to sine of x? Or is it equal to sine... Wait, I'm actually... How did I never think about this? Is... Oh, why would they do that? I hate that. I really prefer it's... Okay. Yeah. The right-hand side of this differential equation is positive. Is positive except if y is equal to n pi. N pi for any integer n. These special lines correspond to equilibrium solutions. Okay, so we have an infinite number of equilibrium solutions. That's interesting. Okay. Between these equilibria, solutions must always increase from the slope field. We expect that their graphs either lie on one of the horizontal lines or increase from one of these lines to the next higher as t goes to infinity. Hence, we can predict the long-term behavior of the solutions even though we cannot explicitly solve the equation. I like that example. Okay. Power of geometry. Using slope fields instead of analytic for y dot equals exp y squared over 10 times sine of y squared. Okay, so that's a really cool example, actually. A case that has not only infinite number of equilibrium solutions, but in between the equilibrium solutions are these logistic type, or whatever, sigmoidal type thing. I don't know what the actual character of it is, but although the computer pictures of solutions of this differential equation are convincing, some subtle questions remain. For example, how do we really know that these pictures are correct? In particular, for the one we just looked at, how do we know that the graphs of solutions do not cross the horizontal lines that are the graphs of the equilibrium solutions? Such a solution could not cross these lines at a non-zero angle, since we know that the tangent line to the solution could not cross these lines at a non-zero angle. What does that even mean? Since we know that the tangent line to the solution must be horizontal. But what prevents certain solutions from crossing these lines tangentially and then continuing to increase? We can eliminate these questions for the simpler model because we can evaluate all of the integrals and check the accuracy of the pictures using analytic techniques. But using analytic techniques to check our qualitative analysis does not work if we cannot find explicit solutions. Besides, having to resort to analytic techniques to check the qualitative results defeats the purpose of using these methods in the first place. In section 1.5, we discuss powerful theorems that answer many of these questions without undue effort. Okay. Nice. All right, revisiting the mixing problem. Recall in the previous section we found precise analytic solutions for the differential equation the amount of sugar, the change in the amount of sugar with respect to time is equal to 2,000 minus 3 times the current amount of sugar over 100, where S describes the amount of sugar in a vat at time t. We found that the general solution of this equation was that, where C is an arbitrary constant. Using slope field for this equation, we can easily derive a qualitative description of these solutions. Okay, we display the slope field and graphs of selected solutions. Note that as expected, the slope field is horizontal if right, let's find the zero of that thing. So if we have 0 is equal to 2,000 minus 3s over 100, then we're going to get 2,000 over 3. Yeah, so that's the 0. Okay, great. So that's a 0. The slopes are positive if it's less than that and negative, and they approach exponentially. So we expect solutions to tend toward the equilibrium solution as t increases. This qualitative analysis indicates that no matter what our initial amount of sugar, the amount of sugar in the vat tends to that amount as t goes to infinity. Of course, we attain the same information by taking the limit of the general solution as t goes to infinity, but it is nice to see the same result in a geometric setting. Furthermore, as in other examples, taking such a limit may not be as easy as in this case. But qualitative methods still may be used to determine the long-term behavior of solutions. Okay. All right, the next model that we're looking at in section 1.3, the RC circuit. Okay, so we have a voltage source, we have a resistor and a capacitor. The simple electric circuit pictured in 1.25 contains a capacitor and a resistor and a voltage source. The behavior of the resistor is specified by a positive parameter R, and thank you, Asset Aksholakov. Alright. The behavior of the capacitor is specified by a positive parameter C, which is the capacitance. Okay. The input voltage across the voltage source at time t is denoted by V of t. This voltage source could be a constant source, such as a battery, or it could be a source that varies with time, such as an AC current. AC current. You know, AC current is a weird way to say that. In any case, we consider the voltage of with respect to be a function that is specified by the circuit designer. In other words, it is part of the design of the circuit. The quantities that specify the behavior of the circuit at a particular time t are the current I of t and the voltage across the capacitor, V sub C of t. In this example, we are interested in the voltage V sub C of t across the capacitor. From the theory of electric circuits, we know that V sub C of t, I'll just say VC. VC of t satisfies the differential equation. RC dVc dt plus Vc is equal to V of t. Let's figure that out. Okay. So we have RC dVc dt plus Vc is equal to V of t. I always forget. I don't know how many times I've looked at the differential equation for okay, but I mean it's this. Hold on. This is an RC circuit, but I forget. There was something in the art of electronics that I'm trying to remember. The change in the voltage. Let me see. Okay, yeah. So for capacitor, the V dot, or let's just say VC dt, dVC dt is equal to I of t over C. I always have to reason about these for so long. And then you just switch it. So for an inductor, dIL dt is equal to the voltage at the current time over L, which is the inductance. So let's say the current is flowing at 1 amp. Then the voltage grows by so as long as the current keeps flowing into it, the voltage keeps going up. So if alright, let's keep going. Alright. So that's what I wanted to review. Alright. Oh, that's nice. Okay. Alright, Okay, so let me write down what they have. So in our normal way of writing it, we have dVC dt is equal to V of t minus VC over RC. So so 3 different voltage sources. If V of t is the zero function, then VC dot equals minus VC over RC. So it's going to decay exponentially to 0 or increase to 0. But it's going to go to 0 no matter what. Oh wow, I didn't even read that, but yeah, that's exactly right. Okay. Cool. Okay, now number 2, so this is going to be 1, 2. V of t equals K, constant voltage source. So now we're going to get VC dot equals K minus VC over RC is equal to. So how are we going to do this? Right, so this is now going to give the graph, because we can see that if K equal to VC, V dot equals 0, equilibrium, solution. So we're good. On-off voltage source. Okay. I thought they were going to do some cool alternating current thing. Alright. Flashing light. Okay. Okay. Let me read this. Alright. The circuit in 125 can be modified to produce a flashing light, such as those used on cell phone towers and flashing road hazard signs. The switch periodically opens and closes. It is open for an interval of time TO. The letter O stands for open. The constant TO is not an initial value. After the switch is open for the initial interval TO, the switch closes and remains closed for a different and shorter interval TC, where the letter C stands for closed. When the switch is open, the capacitor is charging according to the equation. Okay. At time TO, the switch closes and the light turns on. When the lamp is lit, it acts as a resistor in parallel to the other resistor. Let RL be the resistance that is due solely to the lamp. Let RL be the resistance that is solely due to the lamp. It can be shown that the differential equation that governs VC over the time interval between an open and a closed, so while it's closed, is because it's like this: resistor, capacitor, resistor. I was so bad at circuits, man. This gives for V of t equal to K, we get VC dot is equal to K over RC minus R plus R. So this is going to be R, and this is going to be RL, and this is going to be C. So we're going to get RL over R, RL, C, VC. Okay. When combining qualitative with quantitative, when only knowledge of the qualitative behavior of the solution is required, sketches of solutions obtained from slope fields can sometimes suffice. In other applications, it is necessary to know the exact value of the solution within a given initial condition. In these situations, analytic or numerical methods can't be avoided. But even then, it is nice to have graphs of the solutions. Alright. Definitely should do a bunch of these. Euler's method is the only good numerical method. It's pure, you know. The other ones are just too complicated, man. I don't give a frick about no Runge kutta. I don't care about adaptive step sizing. I don't care about BDF methods. I just care about Euler's method. And everything else stinks. Okay, so that is sections 1.2 and 1.3. Let's read through some of the problems. Why not? Okay. Sketch slope fields. Then use a computer to make a slope field. Okay, make slope fields for all of these. Sketch different solutions on the slope field. Oh, this is okay. This is one of those logistic ones. 2y minus t. Okay, we've seen this one before as well. So it's gonna diverge like this, even if they're really close together on this line. Because another way of thinking about this is, as time goes in reverse, these things actually come together. But then they split apart. So this ripple in time is like tearing everything apart. Okay. This one is wonky. So we're getting, if y equals t, if y equals negative t, so let's say, okay, so that's corresponding to this. Oh no, that's the minus 1/2. We need a line. There's a line somewhere. It's going to be this line. So there's this line. Like that. So that's going to be ripping things apart. But if y equals minus 1/2, I'm trying to think. So yeah, I guess this gets pulled apart. These ones kind of come together and then come apart there. This is separable, so we could actually probably figure that one out. Is this one separable? Y squared plus ty, I don't think so. I don't think that's separable. Suppose that we know the function y of ty is continuous. Hold on, let me try to figure that out. If so if changing t, then f anonymous. Autonomous, Jesus. Alright, so in this case, if you can change t and the derivative doesn't change, then you know that this equation is only depending on y. So that means that we can translate it. So A, we can translate it left or right and get a new solution. But basically get the same solution, I think. You know, in other words. What can we conclude about solutions y of t? For example, if y of 0 is less than... B, I don't know the answer to B. Suppose the constant function y of t is equal to 2 for all t. Is it just the constant solution? What does this tell you about the slope field? So if you change t, you can move it up and down. So everything here, there's going to be parallel solutions. There's going to be parallel solutions. So yeah, so this does give you a pretty good idea of so this one we can move left and right. So that means that along these, let me find my drawing of this. So like this way. So then it's got to be periodic or something. Without using any technology. We could probably do this one right now. Alright, so y times y plus 1. So if y equals negative 1, alright, I don't see anything. Alright, so none of them are that. Okay, so this one is going to be y minus 1. So if y equals 1, okay, I don't think it's that one either. Okay, now y squared times y plus 1. So if y equals -1, we should get a horizontal. Oh, okay. Alright, so I don't think it's that one either. Now, 2 minus t squared is going to be equal to square root of 2 minus t plus, square root of 2 plus t. So if t equals plus or minus square root of 2, it should be like right there. Oh, wait. Yeah, I had this all wrong. Hold on. If y equals 0 or -1. Oh, okay. So this one actually is... Wait, but it could be y. It's hard to tell then. I think because of the parabolic nature here that this has to be 3. C is 3, I think. Wait, no, hold on. Actually, I'm so silly. Hold on. I think A is actually 1. I think 1... Three goes to C. 4... Oh, it got sunny. Alright. I think we did enough. Those are the sections.